Welcome to today's lesson in physics. Today we are discussing Bohr model of the hydrogen atom. In the previous lessons, we were discussing Rutherford model of atom and we discussed its drawbacks also. The main drawback of Rutherford model was this: it couldn't explain the stability of atom. In Bohr model, Bohr combined the classical and early quantum concepts and gave his theory in the form of three postulates. Actually, Niels Bohr framed his three postulates from the basis of Rutherford model itself. The foundation of Bohr model also is the presence of nucleus at the center. And he also agrees that the electrons are revolving around the nucleus in some fixed paths. And he stated his postulate 1 as electrons in an atom can revolve in certain stable orbits without radiating energy. So this is how he accounted for the stability of atom. That means, according to Bohr, when an electron revolves around in the stable orbit, that particular electron will not radiate energy. So its energy will be constant in that particular orbit and it will revolve continuously. So according to this postulate, each atom has certain definite stable states in which it can exist, and each possible state has definite total energy. And he called these states as stationary states of an atom. So if an electron is in the stationary state, it will not emit radiation. So there is no problem of collapsing of this electron with the nucleus. Now the second postulate gives where are such stable states or stationary states. According to second postulate, the electron revolves around the nucleus only in those orbits for which the angular momentum is an integral multiple of h by 2 pi, where h is the Planck's constant and its value is 6.6 into 10 raised to minus 34 joules second. So he ruled out the possibility of electron taking any orientation or position around the nucleus. According to Bohr, electrons can revolve around the nucleus only in certain orbits which satisfy this particular condition, and that condition is this, that is, angular momentum should be an integral multiple of h by 2 pi. So in mathematical form, we can write L should be equal to nh by 2 pi, where n can take values like 1, 2, 3, etc. And n is called as principal quantum number. This statement also says that the angular momentum is quantized. You know what is the meaning of quantized? Okay, it changes by discrete values. That's what we mean by quantization. So angular momentum, the quantization of angular momentum, it comes here with the second postulate of Bohr. Now coming to the third postulate, an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. So we have stationary states, and according to Niels Bohr, electron can make transition from a higher energy state to a lower energy state. If such an electron is making transition, that electron will be emitting energy, and that energy comes in the form of a photon. So a photon is emitted having energy equal to the energy difference between the initial and final state. So when an electron jumps, that's what we mean by transition. When an electron jumps from a higher energy state to a lower energy state, it emits energy, and that energy comes in the form of photon. And what is the energy of that photon? Energy of that photon will be equal to the difference in energy between the two energy levels. And we can write that energy of emitted photon, you know how to write the energy of a photon. We write it as h nu, where h is the Planck's constant and nu is the frequency. So h nu is equal to EI minus EF, where EI is the initial energy, that means energy of the electron in the initial state, and EF is the energy of the electron in the final state. So difference in energy comes as the energy of the emitted photon. Now we will discuss how to find radii of Bohr's stationary orbits. Here we use the fundamental concept used by Rutherford itself, that is, the centripetal force for the revolution of electrons around the nucleus is provided by the electrostatic force of attraction between the nucleus and the electron. So if we consider the most fundamental atom, that is the hydrogen atom, we can write mv square by r, that is the centripetal force required, that is equal to 1 by 4 pi epsilon 0 E squared by r square. So E square, there it is, we are having Q1, Q2. Q1 is the charge of the nucleus and Q2 is the charge of the electron. Here both are same in hydrogen atom. So we have 1 by 4 pi epsilon 0 E square by r square. Therefore, we have mv square equal to 1 by 4 pi epsilon 0 E square by r. And from Bohr's second postulate, we know the angular momentum L, it should be equal to nh by 2 pi. And you know what is the expression for angular momentum? Angular momentum, it is r cross p, where p is the linear momentum and its magnitude is rp. So linear momentum, it is mv, and that is how we have L is equal to mvr. So the magnitude of angular momentum, it is mvr. So we have the condition as mvr is equal to nh by 2 pi. So in this equation, we can write V is equal to nh by 2 pi mr. So this V we can substitute in the expression for mv square. So substituting, we have the expression for r, that means substituting for V square, we have m into nh by 2 pi mr whole square is equal to 1 by 4 pi epsilon 0 E square by r, or m into n square h square by 4 pi square m square r square equal to 1 by 4 pi epsilon 0 E square by r. Now doing the necessary cancellation and the simplification, we have the radius as r is equal to epsilon 0 n square h square by pi m E square, or in general form we can write Rn as epsilon 0 h square by pi m E square into n square. The quantity given in bracket, it is constant because epsilon 0 is constant, h constant, pi m, m is the mass of the electron, and E also constant. So that quantity within the bracket is constant, that into n square, which means that radius of the electron, it is directly proportional to square of that n. That n we called as the principal quantum number, or we can state Rn is proportional to n square. So the radii of stationary orbits are in the ratio 1 square is to 2 square is to 3 square, means 1 is to 4 is to 9, etc. That means the stationary orbits, they are not equally spaced. The radii, they are in the ratio 1 is to 4 is to 9. Now, by calculating the value of the quantity within bracket, we have that quantity within bracket as Bohr radius. That means in the previous expression, if we put n equal to 1, we know that radius, that is the most fundamental radius, and that is called as the Bohr radius, represented by A0. So Bohr radius is always represented by the letter A0, and that is h square epsilon 0 by pi m E square. Substituting the values, we have that Bohr radius as 5.29 into 10 raised to minus 11 meter. So in terms of that Bohr radius, we can write the expression for nth orbit in the hydrogen atom as Rn equal to A0 n square. Now coming to the velocity of the electron in an orbit. So everything we are explaining in the case of hydrogen atom because that is the most simplest atom. So from the previous discussion itself, we had this expression, that is mv square equal to 1 by 4 pi epsilon 0 e square by r. And the second postulate of Bohr also we have, that is mvr is equal to nh by 2 pi and v is equal to nh by 2 pi mr. And we obtained r as epsilon 0 n square h square by pi m e square. So substituting r in this expression for v, we substitute r, we have v is equal to nh by 2 pi m into epsilon 0 h square by pi m e square into n square. So that term comes in the denominator. Now again simplifying, we have the expression for v as e square by 2 epsilon 0 nh, or generally we can write Vn is equal to e square by 2 epsilon 0 nh, which means that in the nth orbit, the velocity of the electron, it is inversely proportional to n. So Vn is equal to e square divided by 2 epsilon 0 nh. Now coming to the total energy of the orbiting electron. The first steps we have already discussed in Rutherford model also. You know, for an orbiting electron, we have the centripetal force is equal to Coulomb force of attraction. That is mv square by r equal to 1 by 4 pi epsilon 0 e square by r square, from which we have mv square equal to 1 by 4 pi epsilon 0 e square by r. From this expression, we get an expression for kinetic energy, that is K is equal to half mv square, that is E square divided by 8 epsilon 0 r. That is the expression for kinetic energy. And from electrostatics, we can write the expression for potential energy, that is minus E square by 4 pi epsilon 0 r. So I repeat, we are discussing everything in the case of hydrogen atom, the simple atom. Therefore, the total energy is given by K plus U, that is E square by 8 pi epsilon 0 r minus E square by 4 pi epsilon 0 r, which gives the total energy as minus E square by 8 pi epsilon 0 r. And you know, r is equal to epsilon 0 n square h square by pi m e square. So substituting the value of r, we get E as minus E square divided by 8 pi epsilon 0 into epsilon 0 n square h square by pi m e square. So simplifying the final expression for energy, it comes out to be minus me raised to 4 divided by 8 epsilon 0 square h square n square. So as we know, the terms like m, e raised to 4, 8, epsilon 0 square, h square, all those terms are constants. So substituting their values and converting it into electron volt, we have the simple equation for the energy of the electron in the nth orbit as En is equal to minus 13.6 by n square electron volt. So this expression gives the energy of an electron in the hydrogen atom in the nth orbit, that is minus 13.6 by n square electron volt.